Hi, my name is Carl Rodriguez, and I'm a graduate student at Northwestern University. I'm studying astrophysics, but I do astronomy a little bit differently than most people. Instead of using giant telescopes to explore the universe, I use giant computers to run massive simulations. Today, I'm going to be talking about how black holes move in the center of star clusters. Let's take a look.
If you look out into space, you can see some of the hundreds of billions of stars that make up our galaxy. But if we look closer with the aid of a telescope, we can see that some of the stars aren't single stars at all, but collections of hundreds of thousands of stars clumped together. These globular clusters, like the one we call M22 here, were first discovered over 300 years ago. Since then, we've discovered more and more globular clusters in our galaxy. At this point, we're up to about 150. And as our telescopes have gotten better and better, we've been able to zoom in further and further into these globular clusters until we can see the individual stars within them. But what about the things we can't see? When a massive star dies, it can explode and leave behind a black hole. Now, a black hole in space acts like a bowling ball on a trampoline. It curves it and pulls everything else towards it. But while you can always get off a trampoline, a black hole curves space so much that nothing, not even light, can ever escape. Instead of trying to see something that doesn't want to be seen, sometimes it's easier just to make our own star clusters.
Here at Northwestern, we use supercomputers like this one here to simulate what globular clusters have looked like over billions of years. Computers like this are virtual laboratories, allowing us to grow our own star clusters over billions of virtual years. We start off with what we think a globular cluster looked like when it was formed nearly 12 billion years ago. Things like, how many stars did it have when it was born, and how many of those exploded and collapsed into black holes? Then we let the computer do its thing and calculate how the gravitational pull from every star in every black hole affects every other star in black hole. And if we spread that computation out over hundreds of computer cores, we can watch what happens to a cluster of 1 million stars over 10 billion years, using only a month of time on the computer. Now, the downside to doing everything on a computer is that we don't get any beautiful telescope pictures of clusters, but the upside is really cool CGI.
This is a small collection of some of the stars and black holes from one of our models, sped up so we can see how they move over about 5 million years. You can see as the stars fly around the cluster, pulled by the gravity of every other star. But since we've cooked up this cluster from scratch, we can follow the black holes as well. We've exaggerated how much a black hole warps light around itself, giving us a better look. As we zoom into the center of the cluster, you can see how they dance and move around one another, getting faster and faster the closer to the center we get. Eventually, two of our black holes will wander just a little too close to each other, and they'll get sucked into an orbit around one another, forming what we call a binary black hole. You can think of globular clusters as astronomical factories for binary black holes.
Now you may be thinking, this is all neat, but black holes don't emit light the way stars do. How are you ever going to see them? Let's go back to the analogy with the trampoline. Imagine I've got my bowling ball black hole in the center of my trampoline. Now, let's say I try to roll a smaller black hole, like a tennis ball, across the surface. What's going to happen? Well, the tennis ball is going to get sucked into the sunken part of the trampoline, and it's going to get pulled into an orbit around the bowling ball, kind of the same way that the Earth orbits around the sun in the solar system. But let's take the analogy one step further. If this really were a trampoline and you were sitting on the edge of it, you'd be able to feel the trampoline bounce up and down as the tennis ball goes around the bowling ball. It turns out that when two black holes orbit around one another, they cause the same kind of ripples in space-time. We call these ripples gravitational waves, and they're about to be the new frontier in astrophysics. But the crazy thing is, we think we can actually detect these ripples in space. Down in Louisiana and up in Washington State, a collaboration of over 900 universities, including Northwestern, are currently building a pair of giant gravitational wave detectors, basically giant instruments designed to see these waves as they pass through the Earth. And when they do, we'll have our first direct detection of black holes orbiting around one another that have been formed in the center of these star clusters.